Section 4.2, the mean value theorem. From the last section, we got an idea of where to look for extreme values by finding where the derivative, f prime of x, was equal to 0. We continue that conversation with the following theorem. Rolle's theorem. Let f be a function that satisfies the following. F is continuous on a closed interval ab. F is differentiable on the open interval ab. And f of a is equal to f of b. So given those three things, Rolle's theorem then says there is a number c in the interval ab such that f prime of c is equal to 0, meaning there is some place in that interval where the derivative is equal to 0. So there's a few pictures that we can use just to understand how this might relate to things that we've seen before. So if you think of where you would have some turning points, where the function, say, is going up, but then coming back down again, like a quadratic that is opening down, we've seen that at the vertex, or the top of that, that's where the derivative is equal to 0. We've seen that with trigonometric functions, where the sine or cosine, again, can go up, and then down, and then back up again, and again, at those turning points, that's where the derivative is equal to 0. Even simpler than both of those, if you just think of a horizontal line. A horizontal line is a function, and it's horizontal the whole time, so its derivative everywhere would be 0. That's just related to the derivative of a constant being 0. Let's also recall the intermediate value theorem from Chapter 2. We used it to determine if there was a root to an equation between two numbers. We're going to answer a similar question now with Rolle's theorem. So this example says, prove that the equation x cubed plus x minus 1 equals 0 has exactly one real root. So first of all, from what we learned in Chapter 2, by the intermediate value theorem, we can find a root by just taking a look at two particular numbers. So I just said, how about we look at x equals 0 and x equal 1? You might ask, why did I choose those? Well, f of 0, if I plug 0 into the function x cubed plus x minus 1, I would get 0 plus 0 minus 1, which means f of 0 is negative 1. And if I plug in 1 to that polynomial, x cubed plus x minus 1, I would get 1 plus 1 minus 1, which is 1. So I see that f of 0 is negative 1, and f of 1 is 1, which means that f of x equal to x cubed plus x minus 1 has to cross through the horizontal axis at some point. So there is a value c where, and this should say c is between 0 and 1, such that f of c is equal to 0. So now what we want to show is that there is only one real root. So we want to show that there's only one root over the whole domain. So we just found that there is one between 0 and 1, but we want to show that that's the only thing. As a little bit of a picture, what you're essentially saying is, here's x equals 0, there's x equal 1. This graph, we are saying, only passes through once and never goes back through the x-axis at any other point in the domain. So, to show that there's only one root, let's suppose that there are two roots. So this is a classic way of proving something. Suppose the opposite. Suppose that there's more than one root. So let's just say that there's two, and let's call them a and b. If those are both roots, that means that f of a is equal to 0, and also f of b is equal to 0. Since f is a polynomial, we know that it is differentiable on the open interval ab, and we also know that it is continuous on the closed interval ab. So we just now have those first three things in Rolle's theorem. We need differentiable, continuous, and we need that f of a is equal to f of b. So by Rolle's theorem, there is a number d in that interval such that the derivative of f when evaluated at d is equal to 0. However, if we take our function f of x equal to x cubed plus x minus 1, its derivative is f prime of x equal to 3x squared plus 1. So if we set 3x squared plus 1 equal to 0, we're trying to find out when is that possible. But this would mean that x squared is equal to negative 1/3, which has no solution, meaning no real solution. And we're trying to think of this graphed on the real coordinate plane. So that becomes a contradiction of Rolle's theorem, the fact that we can't solve that. And we can't contradict a theorem that is true. So the assumption that we made that there are two roots is actually incorrect. So we just proved by contradiction that there is only one root, and we know that it exists between 0 and 1. So that's an application of Rolle's theorem, relates to what we saw before with the intermediate value theorem. But more importantly, Rolle's theorem is used to prove this important theorem, the topic of this section, the mean value theorem. The mean value theorem states, let f be a function that satisfies the following. F is continuous on the closed interval ab, and f is differentiable on the open interval ab. Then the conclusion to the theorem says this, then there is a number c in ab such that f prime of c is equal to f of b minus f of a divided by b minus a, or we could also rewrite that as f of b minus f of a is equal to f prime of c times b minus a. As an understanding of this theorem, geometrically, this means that there is some point c comma f of c on the graph where the tangent line is parallel to the secant line. If you take a look at this first version, what's on the right, f of b minus f of a divided by b minus a, that goes all the way back to chapter 2 when we looked at the slope of a secant line. So this is saying that the slope of the tangent line, that's f prime of c, is equal to the slope of the secant line, which means that those two lines are parallel. As a concept, what the mean value theorem tells us is there is a place in the interval where the instantaneous rate of change is equal to the average, or in other words, mean rate of change. So that's where the title mean value theorem comes from, average value theorem. So to understand that, here's a really simple example. Imagine you drive 100 miles in 2 hours. The average speed of your trip would then be 50 miles per hour. Because you drove 100 miles and that happened in 2 hours, your average speed is 50 miles per hour. So if you think about that trip, do you think your speedometer ever displayed 50 miles per hour during that trip? If it didn't, so what if you assumed it never read 50 miles per hour? It was always less than 50 miles per hour. Could you have actually traveled 100 miles in 2 hours? So the answer to this last question, of course, is no. If it didn't display 50 miles per hour, there's no way you could have traveled 100 miles in 2 hours. So this example is saying at some point your speedometer had to have been in the 40s and then crossed over 50 miles per hour and gone above. That's how we get this idea of average speed of 50 miles per hour. So before we look at some other examples, let's look at a proof of the mean value theorem. So first we're going to start with a function y equal f of x. So I'm just going to draw a curve a little bit similar to what we had before. So I'm going to think of a curve like this. So here this is y equal f of x. And we want to consider the secant line between points a f of a and b f of b. So I'm just going to choose these points here. Notice this is a little bit different from Rolle's theorem because the values of those functions, or the function values at those points are not equal. So here's b comma f of b, and then up here is a comma f of a. We're also going to consider the function h of x, which will be the difference between the function and the secant line function. So, just visually, h of x you can think of as the blue curve for f of x minus the red line for the secant line. So that's h of x. The equation of the secant line in point-slope form is y minus a y value, like f of a, equal to the slope, which again, here's the slope of the secant line, f of b minus f of a divided by b minus a. And then that slope is being multiplied by x minus a, x minus an x value. We could rewrite that as what we have here, y equal f of a plus f of b minus f of a divided by b minus a times x minus a. Thus, h of x being the difference of the original function, f of x, and the secant line, means what I just wrote in the box there, means that we could actually rewrite h of x as f of x minus, here's the whole expression that I just boxed up. And rearranging that, I could write it in this form, f of x minus f of a minus the fraction f of b minus f of a over b minus a times x minus a. So now let's notice h of a is equal to 0. If you plug in a into what we said h of x is, that means I would have f of a minus f of a, of course that's 0, minus the secant slope, f of b minus f of a divided by b minus a, but then that would be times a minus a. Which is just 0. So this becomes 0 minus 0, that's 0. That's why I'm saying that h of a is equal to 0. If you plug in b, you would have f of b minus f of a, and then minus that same fraction that would have the denominator of b minus a times b minus a there, and so again we would get something minus itself, and that would end up being 0. So by Rolle's theorem, this means that there has to be a value x equals c in the interval ab such that the derivative of h evaluated at c is equal to 0. So let's actually find the derivative of h of x. The derivative of h of x would be f prime of x minus the derivative of f of a, which is 0, and then minus the slope of the secant line, which is just f of b minus f of a divided by b minus a. So by Rolle's theorem, if I plug in c for x, this means that f prime of c minus the secant slope is equal to 0, which means exactly what we wanted. F prime of c is equal to the slope of the secant line. So that's a proof of the mean value theorem. It's good for you to see a few of these proofs. You, of course, aren't going to have to repeat this, but you should walk yourself through this and just make sure you understand the points from this. So now let's look at an example. Consider f of x equal to x cubed minus x and a equals 0 and b equal 2. Find the number c in the interval 0, 2 such that f prime of c is equal to f of b minus f of a divided by b minus a. So first let's find a few things. The derivative of f. That would just be the derivative of x cubed, which is 3x squared, minus the derivative of x, which is 1. We also need to know what is f of b and f of a. So f of b is just f of 2, which is 2 cubed minus 2, so 8 minus 2, which is 6. And f of a is f of 0, which is 0 cubed minus 0, which is 0. So then f of b minus f of a divided by b minus a would be 6 minus 0 divided by 2 minus 0, which is 4. So then we're trying to find a number c that solves this equation. F prime of c equal to that number 4 that we just got. So f prime of c would be 3c squared minus 1, and we would just set that equal to 4. So this gives us 3c squared equal to 5, c squared equal to 5/3, which means that I either have c equal to positive square root of 5/3 or c is equal to negative square root of 5/3. And so clearly the one that answers our question is c equal to positive square root of 5/3, since this is approximately equal to 1.29. That's the value that's between 0 and 2 that satisfies what we wanted. All right, for another example, if f of 1 is equal to 10 and the derivative of f prime of x, is greater than or equal to 2 for x between 1 and 4, how small can f of 4 possibly be? So first of all, we're given the derivative is greater than or equal to 2 for x between 1 and 4, which means that f is differentiable in that closed interval 1, 4. And since if a function is differentiable, it means that it's continuous, we now also have that f is continuous. So those are the two things that we need for the mean value theorem. So the mean value theorem then says that we're guaranteed there is a number c in the interval 1, 4, such that, and here's the alternate version that we saw in the theorem, f of 4 minus f of 1 equals f prime of c times 4 minus 1. So then f of 4 is the same thing as 4 minus 1, or 3, times f prime of c, plus f of 1, and then substituting what we know f of 1 is, f of 4 is equal to 3 times f prime of c plus 10. Since we were told that the derivative is greater than 2 in that whole interval, then the smallest that the derivative could be is 2, which means that f of 4, the smallest it could be, would be 3 times 2. Here I just replaced the derivative with 2 plus 10, or 16. That's kind of an odd example to look at, but the point of that example is what I've written here. What we are saying with these examples is that we can obtain information about a function by using some information about its derivative. This is an important point for the rest of Chapter 4. We're going to see some things about graphing specifically, where we use information about the derivatives to get information about the function. So then two final results to close out this section. First, a theorem. If f prime of x is equal to 0 for all x in an interval ab, then f is constant on ab. Proof. Let x1 and x2 be any two numbers in the interval ab, where x1 is less than x2. So if you think of a number line, you could say there's a, there's b, and x1 and x2 are just somewhere in between those two. Since f is given as differentiable on ab, then it is differentiable, of course, on the smaller interval x1, x2, which then, of course, means that it's continuous on x1, x2. Thus, by the mean value theorem, there is a value c in the interval x1, x2, so you could say there's c, such that f of x2 minus f of x1 is equal to f prime of c times x2 minus x1. But since we were told that the derivative is equal to 0 for all values between a and b, then this is telling us that f of x2 minus f of x1 is equal to 0, which means f of x1 is equal to f of x2. Since x1 and x2 were arbitrary, this means that f is constant for all values on ab. As a follow-up, a corollary, if f prime of x is equal to g prime of x for all x in an interval ab, then f of x minus g of x is constant on ab. This means we can represent one function, like f of x, as the other one plus some constant. So f of x is equal to g of x plus c. This means that f of x and g of x are in the same family of functions. This is going to be important for us in Chapter 5. So you can make a note of that now. When we start looking at what are called integrals, this will become important.